Section: Introduction. In this section, we explore how reinforcement learning (RL) can be enhanced by using gradient boosting trees (GBT). RL has proven to be effective in tasks requiring sequential decision-making. However, real-world scenarios like inventory management, traffic signal optimization, and robotics involve structured observations with different data types. These tasks can benefit from running on edge devices due to limited resources. Interpretability is crucial in these applications for regulatory compliance and trust in decision-making. Current neural network (NN) solutions struggle with interpretability, handling categorical data, and being light enough for low compute devices. Gradient boosting trees (GBT) are known for their simplicity, accuracy, and ability to handle structured and categorical data well. Despite their success in supervised learning, GBT has not been widely used in RL due to challenges with dynamic datasets and a lack of benchmarks for structured data. We introduce gradient boosting reinforcement learning (GBRL), a GBT framework tailored for RL. Our contributions include demonstrating the effectiveness of GBT in RL tasks and implementing GBT-based versions of popular RL algorithms like A2C and AWR. We show that GBRL can compete with NNs in various environments and outperform them in tasks involving categorical data. We also introduce a tree-based actor-critic architecture based on GBT, which reduces memory and computational requirements, making it more efficient for solving complex RL tasks. Additionally, we provide a modern GBT-based RL library optimized for RL tasks, which integrates seamlessly with existing frameworks like Stable Baselines 3. Recent advancements have expanded the use of GBT beyond traditional regression and classification tasks. GBT has been applied to ranking problems, probabilistic predictions, and uncertainty quantification. While GBT's versatility has been explored in various areas, its application in RL is still relatively unexplored. Previous works have used GBT in off-policy RL methods and bandit settings, but scalability and effectiveness in complex RL environments remain a challenge. Our work demonstrates how GBT can be adapted successfully to solve large-scale RL problems. Interpreting NNs can be complex due to their nonlinear nature, requiring sophisticated methods. In contrast, GBT's decision tree structure allows for faster and more accurate interpretability methods. While NNs excel in capturing complex patterns in high-dimensional data, GBT often perform equally well or better on structured and categorical datasets. We also leverage the framework of functional gradient ascent to adapt GBT to RL, enabling seamless integration of GBRL into existing RL optimization packages. Section Summary. In this section, we introduce Gradient Boosting Reinforcement Learning (GBRL), a framework tailored for RL that leverages gradient boosting trees (GBT) to handle structured and categorical data efficiently. Our contributions include demonstrating the viability of GBT as function approximators in RL, introducing a tree-based actor-critic architecture to reduce memory and computational requirements, and providing a modern GBT-based RL library optimized for CUDA hardware acceleration. Despite the challenges of applying GBT in RL due to distribution shifts and lack of benchmarks for structured data, our work showcases the potential of GBT in solving complex, high-dimensional RL tasks effectively. Section: Preliminaries. In this section, we introduce Markov decision processes (MDPs) and the actor-critic (AC) schema. We also discuss gradient boosting trees (GBT) and how we combine these concepts to create gradient-boosted reinforcement learning (GBRL). In a Markov decision process, we deal with a system where an agent observes a state, takes an action based on its policy, transitions to a new state according to probabilities, and receives a reward. The goal is to find the best policy that maximizes the expected reward over time, considering a discount factor. We use functions like the action value function to estimate returns, the value function to predict returns, and the advantage function to compare the benefits of different actions. Actor-critic reinforcement learning combines policy and value learning. In GBRL, we enhance AC algorithms like A2C, PPO, and AWR to work with GBT-based function approximators. These methods improve stability, reduce variance, and enhance sample efficiency in learning tasks. Gradient boosting trees are a machine learning technique that combines decision trees with gradient descent. GBT models predict outputs by adding multiple trees together. In functional gradient descent, we aim to minimize the expected loss by iteratively adding trees to our model. We update our model by taking steps in the direction of the functional gradient, constrained within the decision tree function class. Section Summary. In this section, we introduce Markov decision processes, MDPs, and the actor-critic, AC, schema, followed by gradient boosting trees, GBT. We then combine these paradigms to create gradient-boosted reinforcement learning, GBRL. MDPs involve agents observing states, taking actions based on policies, transitioning to new states with rewards, aiming to find optimal policies for maximizing expected rewards. AC methods learn policies and values, with GBRL extending AC algorithms to incorporate GBT-based function approximators for improved stability and efficiency. GBT combines decision tree ensembles with functional gradient descent to iteratively minimize expected loss over datasets, predicting outputs using additive trees and functional mappings. Section: Gradient Boosting Reinforcement Learning. In this section, we extended the gradient boosting trees, GBT, framework to support actor-critic, AC, algorithms in reinforcement learning, RL. Our goal in RL is to maximize the return, which is the total reward an agent receives over time. Unlike supervised learning, RL involves learning through trial and error without known target predictions beforehand. In our approach, we use the gradient of the return with respect to the policy to reinforce good actions in RL. We optimize the objective directly over a class of decision tree functions by iteratively growing a collection of trees. These trees output parameters, theta, representing the AC components like the policy and value function. To address challenges specific to RL, such as non-stationary state distribution and online learning, we incorporate techniques from neural networks, NN, and GBT literature. We update the ensemble at each iteration by fitting a decision tree on a randomly sampled batch from the experience buffer. This helps handle varying gradients and improves stability during training. In GBRL, we predict both the policy and value estimate using a shared tree structure, reducing memory and computational requirements. By applying different learning rates to the policy and value outputs, we can effectively optimize distinct objectives within this shared structure. Our experiments focus on evaluating the effectiveness of GBT-based AC algorithms in solving complex RL tasks, comparing GBRL with nitrogen mononitride-based approaches, exploring the benefits of GBT in categorical domains, and assessing the impact of sharing the tree structure between the actor and the critic. We implemented and tested GBRL versions of A2C and AWR in various RL environments, comparing them with NN implementations. We provide detailed results, including learning curves, implementation specifics, and hyperparameters in the supplementary material. Section Summary. In this section, we extend the gradient boosting trees, GBT, framework to support actor-critic, AC, algorithms in reinforcement learning, RL. Our approach optimizes the return by iteratively growing an ensemble of decision trees that directly optimize the objective over the decision tree function class. To address challenges unique to RL, such as non-stationary state distributions and online learning, we employ tools from neural networks, NN, and GBT literature, utilizing batch learning and differentiated learning rates to enhance stability and performance in RL tasks. Section: Classic Environments. In this section, we assessed GBRL's performance in various RL tasks across different environments provided by GIM. We trained our agents for a specific number of steps and presented the outcomes in figures and tables. When comparing GBRL with NN in terms of optimization, we found similar performance in some cases, while in others, GBRL outperformed NN, such as in the mountain car environment. However, in Pendulum, NN showed better results. Moving on to high-dimensional vectorized environments like football and Atari RAM, we observed that GBRL excelled in the football domain due to its structured data handling capabilities, outperforming NN in most cases. On the other hand, in the unstructured Atari RAM domain, NN generally performed better, except for AWR where GBRL showed better results. In categorical environments like mini-grid, where structured data is crucial, GBRL outperformed or matched NN in most tasks, showcasing its strength in handling structured data effectively. When compared to traditional GBT libraries like CatBoost and XGBoost in the CartPole v1 environment, GBRL efficiently solved the task within a reasonable timeframe and remained competitive with NN across various environments. Furthermore, we evaluated the benefits of using a shared AC architecture in GBRL by training agents on mini-grid environments. The shared structure significantly reduced GPU memory consumption and improved computation speed without compromising performance. In summary, GBRL demonstrated varying performance across different RL algorithms, excelling in structured and categorical environments like mini-grid. On the other hand, it underperformed in unstructured environments like Atari RAM. These results align with previous findings suggesting that NNs are better suited for smooth solutions, while GBTs excel in handling irregular patterns and categorical data, explaining GBRL's success in specific environments. Overall, GBRL proved to be a strong candidate for structured data tasks, showcasing its incremental learning strategy and outperforming other algorithmic backbones in certain environments.